We were looking at this question related to an exponential random variable wherein we have done part A. Now we want to look at part B. Part B says that we want to find the conditional probability that the repair takes at least 10 hours given that its duration exceeds 9 hours. Let's just recall in part A we already defined the random variable x. So this is what we did already in part A. Denote the time in hours required to repair a machine, right? Because that's what we're interested in, right? The time in hours required to repair a machine is an exponentially distributed random variable. So we're just going to name it in hours required to repair a machine. So we're just naming the random variable x. We already did this in part A. This is just a refresher. And x is exponentially distributed with parameter lambda is 1 by 2. Now we want to look at part B. We already talked about this in part A. So you want to find the conditional probability that the repair takes at least 10 hours, x is greater than or equal to 10, given that its duration exceeds 9 hours. Remember, with a continuous random variable, equal to sign does not matter when you're finding probabilities, because probability that it's equal to a specific value is always 0, right? Now here what we're going to do is we're going to use the memoryless property of exponential random variable, based upon which I can write this as simply as probability x is greater than 10 minus, again equal to sign does not matter when you're dealing with a continuous random variable, right? So this is memoryless property of exponential random variable, which is essentially that probability x is greater than s, given x is again equal to sign makes no difference with continuous random variables, whether you write it or not does not matter. Probability x is greater than s minus t, right? So we're applying this memoryless property of the exponential random variable over here, right? We could solve it as a conditional probability, but there's no need. We could apply the definition of conditional probability and solve it, but there's no need. You can use the memoryless property of exponential random variable. So this just simply becomes probability x is greater than 1. To find probability x is greater than 1, um, similar to probability, similar to find probability x is greater than 1, similar to probability x is greater than 2 in part A that we've already done. We can use either approach. We use two approaches in part A and we can use either approach here also. We use either approach. Approach 1 was use the PDF, approach 2 was to use the CDF. Let's use approach 1. So approach 1 is use PDF, right? For this already, though we've discussed this in part 1, but let's see what the PDF of an exponentially random variable is. In this case, PDF of this exponential random variable x, which is a parameter lambda, is 1 by 2. Exponential random variable is of the form fx is equal to lambda e minus lambda x. Lambda is 1 by 2 for x greater than equal to 0 and 0 otherwise. And recall, so in this way, we know we already discussed this in part 1, x takes on all values greater than equal to 0, where its PDF is non-zero. We should always note the values it takes, right? So the values it takes are greater than equal to 0, where its PDF is non-zero. Right, we've already discussed this. So now probability x is greater than 1. We know when you want to use the PDF to find any probability, right? We know when you want to use the PDF to find any probability, we have to integrate the PDF over that interval for a continuous random variable, right? However, probability x is greater than 1, I can write it more specifically as probability x is greater than 1 less than infinity, right? Remember, if you keep in mind the values a continuous random variable takes, you can define its interval probabilities in a more specific manner. Instead of writing probability x is greater than 1, I can add this part. Where did this part come from? This comes from the fact that x takes on all, again the key is all values greater than equal to 0 from the PDF you know. Remember the PDF, uh, through the PDF you can find what values the continuous random variable takes on, which are all those values where its PDF is non-zero. So since it takes on every possible value that is greater than equal to 0, so probability x is greater than 1 is essentially probability x is greater than 1 less than infinity. There's no upper bound, right? It's infinity. Now this makes it a lot easier. Now when you want to, because remember whenever you're integrating, integrating between points A and B, right? When you write integral like this, so you need to know what these 2 points are. I know this is 1. This b now I know is infinity, right? So keeping in mind what values it takes allows you to define the interval more precisely to help do the integration. So now I just, to find the probability it lies in this interval, I'll just integrate the PDF over this interval. And the PDF is 1 by 2 e minus 1 by 2x dx. Now, when we integrate this, I'll just take this 1 by 2 out. 1 by infinity e minus 1 by 2x dx. Sorry, here we'll apply what we know the integral of EAX is, right? So just let's recall, when we integrate EAX dx, the integral just turns out to be EAX by A. And obviously here we don't have limits, so constant of integration would come, but here we won't because we do have limits. Right, so when I integrate this, this would be E minus 1 by 2x divided by minus 1 by 2, 1 to infinity. And then I'll just simplify this a bit, this minus 1 by 2 and then this 1 by 2. So when we simplify this, this becomes minus E minus 1 by 2x. And then it's 1 to infinity. Now it's just time for us to plug in the limits. E power minus infinity is just 0 minus E minus 1 by 2. How do we know this is 0? You can think about it like this, right? This is e minus 1 by 2x, right? And x is going to infinity, right? So there are actually two ways to think about this. One could be, you can think about writing it like this, 1 by e 1 by 2x. As x goes to infinity, we know the graph of e power x is this, right? It's like this. So as x goes to infinity, e power 1 by 2x goes to infinity as well, and 1 by infinity is 0. Or you can think about it like this. The graph of e minus 1 by 2x would be something like this. So as x goes to infinity, e minus 1 by 2x goes to 0. So you can either think about it as it is, e minus 1 by 2x, the graph is something like this. As x goes to infinity, e minus 1 by 2x goes to 0. If you don't want to think about this graph, you can write it as 1 by e1 by 2x. And from here we can see this is the graph of e1 by 2x. If x goes to infinity, e1 by 2x goes to infinity. So 1 by infinity goes to 0. Right? So either way you can think about this. And then this just becomes what sorry, so this will just become e power minus 1 by 2. So this is approach 1 to find this probability. So approach 2 is going to be, we can use the CDF, right? Here we already know what the CDF of an exponential random variable is of the form, so it's easy to either use CDF or to use CDF, right? So let's just recall, we already discussed this in part A. So in this case, the CDF of this exponential random variable is of the form and this is for x greater than equal to 0 and 0 other values. Right, so now we know that the CDF takes this form, we know of an exponential random variable. We want to find the probability x is greater than 1. First, if we want to use the CDF to evaluate this probability, we need to rewrite it in terms of the CDF, right? Because CDF is always probability x is less than equal to x. Right, so I'll write this as 1 minus probability x is less than equal to 1. How do we write this? To rewrite in terms of CDF, we are using complement rule. Because remember the CDF, to rewrite in terms of CDF using complement rule. And remember what complement rule is? Probability of A is 1 minus probability not A. Then equal greater than 1 is 1 minus probability x is less than equal to 1. And CDF, remember, is always the fx is equal to probability x is less than equal to x, right? So we have probability x is greater than 1. If we want to evaluate it using the CDF of x, we need to first use the complement tool to rewrite it in terms of CDF, because CDF is defined in terms of less than equal to probability. So in the case of continuous random variable, less than probabilities, because equal to sign does not matter. Now I've written this in terms of CDF of x, and then I can write this as 1 minus f1. Probability x less than equal to 1 is just essentially f1. We're applying using the definition of CDF. Once we've written it in the form of the CDF, we can apply the definition of the CDF, which is fx is probability x is less than equal to x, right? So probability x is less than equal to 1 is just f1. So now let's see what f1 is. Now we go to our CDF, and we know x is equal to 1 falls in this area of the CDF that's defined, right, where x is greater than equal to 0. So f1 would just be 1 minus, and then now we evaluate f1. 1 minus e minus 1, sorry, e minus 1, sorry, e minus 1 by 2, 1. This is what we have to do, right? So we have to evaluate the CDF. This is the interval that is relevant for x is equal to 1. Right, so over here, we know 1 minus e1 by 2, so this x just gets replaced with 1 to find f1, right? So then we just simplify this, and this also turns out to be e minus 1 by 2. So the two key takeaways from this part: number one, you should remember the memoryless property of exponential random variable, right, which says that the probability x is greater than s given x is greater than t is just the probability x is greater than s minus t. And remember, with continuous random variable, the equal to sign makes no difference. Right, this is something you should keep in mind, and whenever you're finding any probability related to a continuous random related to an exponential random variable, we know what the expression of its PDF and CDF is like, so you can use either. When you're using the PDF, you just have to integrate the PDFs. Right, and when you're using the CDF, you can just use the expression of the CDF. Sometimes how you do have to apply the complement rule to get it in terms of the CDF of x before you can use the definition of the CDF.